Okay, this second video is going to help us understand the equations that we're going to use to help us calculate thermal energy transfer. So we're going to use this equation. There's a lot of new symbols here, so it looks scary, but it's not that scary. So our letter or symbol that we use for energy transfer is Q. So that represents joules, and we've used joules before when we talk about energy, like when we calculate work, we're calculating the number of joules that it takes. So anyway, Q is energy transfer. M is the mass of the material involved. C is the specific heat capacity, and this is just a number that you look up. So every object heats up faster or slower than others. So for example, metal heats up pretty quickly, which is why we use it for, pots for cooking. But water takes forever to heat up and cool down. So water has a very high specific heat compared to something like aluminum. And then this triangle is called delta, and then we've got the letter T. So it's called delta T, which is the change in temperature. So basically what this is saying is if we want to figure out how much energy is transferred, then we need to figure out how big an object is, what it's made of, and how much the temperature changed, which seems to make sense. So we've got a couple other equations. All of them look kind of scary, but all of them are not a whole lot different than what we have here. So this first one is, the first two actually are other ways to calculate the rate of an energy transfer. So that's also another way to think of power or watts. So this is the exact same power that we calculate when we do work per second, or joules per second. It's just another way to calculate it. So we have energy transfer divided by the change in time, or basically the amount of time it takes to transfer the energy. So Q is the same thing as work, T is the same thing as time, so this is the same formula that we've used before, just with different numbers. Another way to calculate this, we could use K, which is the thermal conductivity, how well something conducts energy, the area of the thermal conductivity, and the change in temperature, and then we divide that by the thickness of the material. So this and this are basically the same thing. They're just different ways to calculate it. And then we could solve for thermal conductivity essentially by rearranging the equation to this over here. So let's do an example. So we've got a metal block. This metal block is made of aluminum, and the temperature of this block is 80 degrees Celsius. And we're going to put it in 1 liter, which is also 1 kilogram of water, which is at 25 degrees Celsius. And so what we want to do is we want to figure out if the water ends up heating up to 30 degrees Celsius, so the water itself went from 25 to 30, then how much energy went from the block to the water. So we're going to use the equation that we just looked at, and the best way to do these equations is to write down everything that we know. So the mass of the water, 1 kilogram. The specific heat of water is 4,184 joules per kilogram per degree Celsius. The change in temperature is the difference between these two, so it changed 5 degrees. The specific heat of aluminum is only 900, so the specific heat of water is way higher than that of aluminum. It's at least 4 times higher. And then the change in temperature for our metal block. So the metal block started off at 80 degrees, and it's going to go until it goes to 30 degrees, because that's our final temperature for everything. So everything's going to be 30 degrees. So it changed 50 degrees. So this is some of the stuff that we know. So the things that we don't know are the energy transfer, and we also never found out the mass of the block. So we're going to select equations to solve for the things that we don't know. So what we can kind of assume is that the energy transfer from the block is the same as the energy transfer to the water. So in other words, the energy that the block lost is the same as the energy that the water gained. So that's that first law of thermodynamics, that energy is conserved. So if we can solve for Q for one of these, then we know what the Q for the other one is. So basically what we're going to do is we're going to solve for the Q, the energy that the water gained, and then we can work backwards and figure out what the mass of the block is. So we're going to use the same equation as before. The Q is, I'm going to back up a little bit here. This one, so we're going to use Q is equal to M times C times delta T. Okay, so Q times M times C times delta T. So the mass of our water is 1 gram, or 1 kilogram, excuse me. The specific heat, and this is just a number that you just look up on a chart somewhere, is 4,184 joules per kilogram. The change in temperature is 5,000 degrees. So that means the water gained 21,000 joules, which means our block lost 21,000 joules. So now what we're going to do is we're going to set up the same equation, but now our Q, we know what Q is because that's what the water gained. It's 21,000 joules, and this evidently they rounded back here and they didn't round here. So anyway, now that we have Q, we already know the specific heat of aluminum, and we know how much the aluminum block changed. So all we have left is our unknown, which is the mass of the aluminum block. So if we rearrange the equation for mass of the aluminum block, plug in everything that we know, the block has to weigh 0.4 kilograms, 0.46 kilograms, or 460 grams. Okay. So this is similar to the practice problem that you need to do on your worksheet. So we've got 1 kilogram of aluminum block. This one is heated at 90 degrees, and it's placed in 4 liters of water, which is the same thing as 4 kilograms of water. And that water is 25 degrees. So based on this information, it's kind of similar to what we just did. You should be able to find what the final temperature of what the water is going to be. So we're going to do the same process. You're going to list all of your known values, list your unknowns, figure out our equation, and then solve for what you need to know. So that's your goal, is to get through number 22, and then we'll do some talk about our big project that we're going to do with thermodynamics.